Yeah, so it's my great pleasure to introduce Matthias Caro today, who's like already one of us in our hearts, so to say, but legally also one of us 6 days from now when he's about to join the group on the 1st of April, which is great. And there's not so much to be said. The talk will speak for himself. But Matthias Caro is like one of the leading experts on quantum assisted machine learning from the mathematical side. He's also coming from the mathematics department in Munich. And yeah, let's keep it short and rather discuss more. And we're very much looking forward to what you have to say or what we together have to discuss in the next minutes.
Okay, perfect. Thanks a lot. Yeah, I'm already very much looking forward to joining you also physically in about a week. But until then, let's do this via Zoom. So my plan for today is to tell you a little bit about different topics in quantum machine learning that I'm interested in. So this will be like something of an overview talk, but please at any point feel free to interrupt me, ask questions, and I can try and give more details. Wonderful. So let's see whether the slide sharing is working. Can you see the slides?
It seems fine.
Perfect. Then I'll get started. So
wonderful.
I won't just talk about my work today, but more about quantum machine learning in general. But as it's natural, I'll tell you a bit about stuff that I've worked on or stuff that I might work on in the future, including joint works with Sean Data, who's currently at Stanford, then your very own Berlin subgroup, and work with Robert Huang and people from Los Alamos. So I'll keep this part very short because in a quantum machine learning reading group, I don't really have to motivate too much, but maybe just to show you how I as a mathematician look at these things. So if I think about machine learning, then I think of it as some kind of a new paradigm of meta algorithms. By that I mean you don't write the algorithm to solve the problem. What you rather write is an algorithm that learns from data and thereby produces an algorithm to solve the problem. And well, the reason why you want to do this is because writing algorithms can be hard, and finding such meta algorithms can help you avoid coding by hand and instead extract rules from data. And now, if you look at this as a mathematician and you dream about this, then what you want to do is to understand the training data requirements and the computational complexity requirements for successful learning. And if you now take a similar perspective on quantum computing, then that's also a new paradigm of computing. This time you kind of change what computers you use, no more classical but quantum mechanical ones. Reasons are manifold. You could say that this should be like the fundamental perspective of computation. The quantum mechanics is fundamental to nature. And again, as a mathematician, what you dream about, well, basically the same thing everybody in quantum computing dreams about, namely find some way of showing guarantees where quantum computing actually outperforms classical computing. All right, now what happens if you throw these two motivation perspectives together? Well, you obviously end up with quantum machine learning, but that's not a particularly well-defined term. So there are many different flavors of QML. Among them are learning-inspired approaches to quantum information problems. I guess one of the most famous ones in this direction is the whole shadow tomography and classical shadows business. Then there's new machine learning models based on quantum computing. So that's variational quantum machine learning and quantum assisted machine learning. And what I personally find pretty exciting are new types of quantum data access. So that means the fact that data can be quantum poses new possibilities, but also new problems that classical data just doesn't have. And probably there's many, many more that I won't really cover today. But as I said, so my goal for today is to give you like an incomplete overview over some of these topics. And it's going to be topics that I've either already worked on or am happy to work on so that it hopefully serves as a basis for discussion. So my plan is to first show off my mathematical side by telling you about classical learning theory. But we can keep this brief because I assume that most of you know a little bit of this already. Then I'll tell you about variational quantum machine learning, which is what I've worked the most on. I'll also tell you a bit about learning classical functions from quantum examples, which is let's say a computer science-y kind of framework. And then I'll tell you about learning quantum objects from quantum data, which is, I would argue, more of a physics perspective on learning problems. And then, but also throughout, a lot of time for your questions. All right, classical learning theory. Let's give you a brief introduction. And I always start my talks about packed learning with this comic, so you might have seen it before, but I will reuse it as much as possible, since it took me ages. So in packed learning, we model our learning problem as follows. So you have a learner, and then somewhere in the world, there's a distribution over inputs x, and there's an unknown function f star, about which you maybe know that it lies in some class f, but nothing else. So both of these objects are unknown. Now, the way the learner gets access to these objects is through training data. And I've so far worked only on supervised learning, so it's labeled training data. That means you get examples of the form xi, f star of xi, so input, output. And now the mathematics or probability theory assumption here is that the inputs xi are drawn identically distributed and independently from this underlying distribution mu. What should you do? Well, given the training data, you should produce a hypothesis. So the hypothesis for the purposes of this talk will always lie in some model class f. For convenience, I've assumed that the unknown function is in the same class f. It's not really necessary for what I'm going to tell you about. Now, of course, the hypothesis shouldn't just be some function. It should be an approximation to the unknown function. But what I want to emphasize is that in packed learning, it's an approximation with respect to the underlying distribution mu. So by that, I mean, if some instances get very low weight assigned to by the probability measure mu, it's not so important whether you approximate the function well on those inputs. On the other hand, the inputs that get a high probability weight should be faithfully approximated. Okay. There are many ways of doing machine learning, but if you want to study sample complexities, it's often useful to go back to the basics by looking at the principle of empirical risk minimization. So empirical risk minimization is based on a simple idea, namely, somewhat underlying is an assumption that the concept class that you're using, so the class of functions that your model can implement, has low complexity. Now, low complexity is not an absolute term, it's relative, namely it's relative to the number of training data points you have. But in that sense, it should have low complexity. And then what you do is you just try and find some function that fits the training data well. And your hope is that that's going to do fine. Now, what I want to show you is how to mathematically formalize this. And maybe as a disclaimer, what I write here is one sentence, like find a hypothesis that fits the training data well, is a very hard optimization problem. But it's one that I often, well, let's say, don't discuss in too much detail because I care about the training data requirements. So what I'm going to talk about today often has the flavor, if you manage to optimize, then I can give you guarantees, but I don't tell you how to optimize. But now, how to mathematically formalize whether empirical risk minimization works. And this is like my favorite definition, I guess, at least for the last few years, so-called probably approximately correct generalization bounds. And I will show you a version here that's called uniform, but that's not so crucial for the rest of the talk. So the ingredients for such a packed generalization bound are the model class F and a loss function L, which compares two labels. So you can think of Y as the label space, and then big loss indicates that the labels are very different. The small loss indicates that they're very similar. So it could, for example, be a distance if you have a distance on your label space, but it doesn't have to be. And a packed generalization bound now looks as follows. So you want a guarantee that works for any possible probability measure P and for any possible unknown function F. And that's because you, in advance, know neither the probability measure nor the function. So it would be nice to have something that works either way. And then what you want is a guarantee that works with high probability over the chosen training data. This is because you could always get unlucky with the training data, but you want that the unlucky cases have low probability. And the guarantee you want is some guarantee that works for all functions in your model class. This is because you don't know in advance what your machine learning model is going to produce. So if you want to be sure, you just want something that works for any possible output. And what you want is a bound of this kind. So here the left-hand side is the true risk. So it's the expected loss of using H to predict, while F star is the true function. And this is what you want to make small. So you want a small expected loss. And what you can do is control this by the training error. So by averaging the loss just over the training data you have available. And then the question is, how much are you losing here? So what do we have to add in this? Here I just denoted by some function g, which is going to depend on, for example, your model class and on the training data size. And the question that I often look at is, what kind of functions g could you pick here? For which can you prove such inequalities? And yeah, the piece of nomenclature is, if you pull this training risk to the left-hand side, the difference is called generalization error. And now to give you like a short glimpse at the techniques that I'm familiar with, I've often used complexity measures to bound these functions. So this is like the standard approach in classical learning theory, I would say. And there's many of those. So there's VC dimension, pseudo dimension, fat shattering dimension, Rademacher complexities, covering numbers, metric entropies, and many more. To give you a short intuition of how at least one of these works, covering numbers. So what you try is you think of your function class as a subset of some overall function space. And now you try to cover the whole function class by epsilon balls with centers inside the class. So take the first ball, take the second and third, and then cover the whole thing. Now, the reason why we call this empirical is because the way you measure distance here is training data dependent. And training data dependent things are often called empirical. So a little bit more precisely, the ambient space is the space of all functions from x to y. The set you're trying to cover is f. And then you use a pseudo metric coming from some semi-norm, which is basically an LP norm. But you should think capital LP, not small LP. But those are details. All right, so these are like techniques in classical learning theory that I know a little bit about. Now, where do I use them? So the first area where we use them is in variational quantum machine learning. Again, I can probably keep the motivation short. So just to recap, variational QML models are basically described by parameterized quantum circuits. And there you have some like trainable parameters, which you can classically optimize. Now, from the mathematics perspective, variational QML model is a parameterized either unitary or, if you include some noise, CP-TP map. And the parameterization arises from the circuit structure. And here, my parameter vector, this alpha, you should think of this as including continuous parameters like angles that you can train, but maybe also discrete parameters like whether you put gates or not, how you can change the structure, and so on. Okay, and then what you do with this is, if you want to use this for machine learning, you use quantum computers to evaluate predictions, loss functions, and their gradients. But you use a classical computer for optimization. And the hope is that this makes this near-term tractable, because
can I ask a high-level question before you go into details? Like, sure. It's a high-level idea slide, so I have a high-level question, which is like, I mean, surely the parameters of the unitaries are like part of the problem. But if you start like seeing the architecture of the circuit as a parameter as well, it might be not so obvious like how to compare like different instances of different system sizes so clearly, right? Because at the end of the day, it's all about scaling, and like how would you make like sense of the idea of like having the same circuit of a kind but just of different sizes? Do you see?
I agree. Like once you introduce varying circuit architectures, it's like more difficult to think of circuit families and to formalize this in a computational complexity language. I think that's correct. But what you could do is, for example, to speak of circuits of, let's say, depth d, and now you could allow all possible structures of circuits up to depth d, and then you have d as the single parameter.
I see. So you would have like another high-level constraint of some sort, so that you can compare different instances. But
exactly, okay. I think that's probably one reasonable way to think about this.
Wonderful, thank you. Great.
Okay, so and this classical optimization of quantum circuits then gives you like a hybrid quantum classical approach where you use classical computers for the optimization, but quantum computers to actually evaluate what you're doing. Okay, in pictures, you can think of something like this. So this is a quantum circuit, surprise, surprise. And I drew it here with two kinds of gates. So the red gates, you should think of as trainable. So that means there are some parameters in there that you can tune. The blue gates are fixed. So I don't know, you could think of a fixed C0 gate or something where there's no natural parameter to tune, it's just a fixed gate that you put in your circuit. So for example, okay, I'm not that good with this language, but I think many people who are interested in like these hardware efficient ansatzes and so, they have entangling layers, and entangling layers are often just like fixed C0 gates or something, so not trainable. And what I want to emphasize is that for my purposes, fixed gates can be whatever you want. So they could be global, like this gate here. However, trainable gates should be local. And by local, I mean k local for some k that doesn't depend on the number of qubits n. So in this picture, all the trainable gates are too local. For purposes of drawing, I drew them geometrically too local, so connecting neighboring qubits. That actually doesn't matter for the proofs. It's just easier to draw. And now, if you want to use this for machine learning, you can feed in a quantum state. You can run it through the circuit, and in the end, you can perform a measurement. And then you can use that measurement result, or maybe variants of it to get gradients to update the parameters. So this way, you can use this as a quantum machine learning model for processing quantum data. But what if you want to do classical data? Well, we have to encode the classical data somehow. And the way this has been done for like, okay, I wanted to say ages, but QML is very young. So let's say in the beginning, was by putting in front of the whole trainable circuit an encoding layer. So this E is some kind of unitary or whatever that depends on the classical input parameters, and then prepare some kind of quantum state. And then you feed that quantum state to the rest. So this is one way of getting in classical parameters, classical inputs. You can now generalize this a little bit by not having a single green encoding gate in the beginning, but by distributing encoding gates throughout the circuit. That's obviously more general than what I showed you before. And it has been observed by several people, some attending the meeting, that this ability to distribute encoding gates and to repeat encoding gates can actually be important for these QML models. So these are like the pictures, but how do you use them to make predictions, and how do you understand what the complexity here is? On a high level, where can the complexity come from? Three obvious sources are the data encoding, the choice of measurement, and the trainable part, so the red gates. And all of these have already been looked at. The orange works are where I was involved. And for example, this is a nice work from the group in Leiden. These works use Rademacher complexities, and this uses a little bit of covering numbers. So, whoops. What I want to show you is to give you like a feeling for the kinds of guarantees we can prove. So the first example that I want to show you is in terms of the trainable part. So these are results from a paper that I had with Sean Data, and then from a paper with Robert Huang and people at Los Alamos. So what we look at is a quantum machine learning model with T trainable local gates. So T of these red gates that we had before. And then what you can show is that the pseudo dimension of the function class you can implement. So I'm being a little bit vague here. Also, I haven't defined the pseudo dimension, but if you know what it means, this scales at most slightly superlinearly in the number of trainable gates. Something similar holds for metric entropies, which are just logarithms of covering numbers. They also scale only slightly superlinearly in T. And using now classical learning theory machinery, you can show that this implies a generalization error bound. Namely, with high probability, if you draw training data of size n, the generalization error can be bounded by something like square root of T log T over n. Why should you care about the bound? Let me just highlight like one possible interesting case. If you have an efficiently implementable quantum machine learning model. So that doesn't even have to be near term, it could be longer term, but as long as it has polynomial size, so polynomially many trainable gates, then this bound tells you that polynomial size training data is going to be enough for good generalization. So in some sense, you get an efficiency guarantee on the training data requirements. Okay, maybe we can keep this for discussion later, but let me already say that these bounds are hiding some ugly constants. You can improve the ugly constants if you make additional assumptions about parameterizations, right? So here I just assume T trainable gates. I don't make any assumptions about how you train them. And still you can prove something, but then obviously it's not going to be tight for special cases. Still, I think if you give me a parameterization, I can make it tighter. I don't think I can make it tight, or at least I wouldn't know how to prove tightness here. So that's, I think, one direction that's still open here. If you care more about data encoding than about
what does it even? Sorry, that's a stupid question, but what does it even mean to be tight?
Yeah.
Can you elaborate on this?
Yeah, that's a very good question. And I'm honestly not sure if there's like a complete answer to this. There are many ways in which this is probably not tight. So tight in the sense of if you look at a specific parameterization, using this bound that works for all possible parameterizations is probably not going to give you the best kind of bound you can prove. And probably you're going to generalize better than what my bound tells you. But also, my bound is this like super worst case thing that works for all possible data generating distributions. Maybe what you care about are specific distributions coming from physics. And then again, I wouldn't expect these bounds to give you the right generalization behavior. But yeah, I'm not so sure how or whether there's a good answer to this question yet.
Okay, but that's a great start. Thanks. Yeah. Okay.
I mean, Matthias, is there like a lot of literature on generalization error lower bounds? Does it even make sense conceptually?
Yeah. It's not so much a general generalization error lower bound. So what I know in the literature, for example, if you look at VC dimension, there are lower bounds that say you need at least this many samples to get good generalization for all possible distributions, because otherwise I can construct a pathological distribution on which you will fail to generalize. So these are the kind of lower bounds I know, but they're very tailored to specific pathological examples.
Good, but I mean, this is like the nature of lower bounds in general.
Yeah, that is probably true. All right.
Yes.
Yeah.
Sorry, I have a question. Do you consider having non-trainable gates as well?
Yes. So for this bound, you can also have like these blue non-trainable gates. Mm-hmm. These are like totally fine, and they don't influence the bound at all. The bound stays exactly the same. So you could have exponentially many fixed gates. The bound doesn't care.
I guess I was curious about why the non-trainable gates don't influence the bound, because they should increase the complexity of the circuit class as well.
Yeah, that's true. And I think that's like another intuition for why these bounds are not tight in general, because like you say, you could probably increase complexity there. The reason why they don't matter on an intuitive level is because on a very high level, the training data gives you information about fixing parameters in a good way. But so the number of parameters that you can fix or that you can vary actually matters. The fixed gates, however, are always the same and you cannot change them. So you don't need training data to learn what fixed gate to choose. Very high level. I could explain it better on the level of the proof, I think, but I don't have slides for the proof.
Thank you.
All right. And if you want, you can play the same game, focusing on the data encoding instead of the trainable gates. So this is what I did with Elias, Johannes, Jens, and Ryan. And what you can do here is to show something with a similar flavor. Namely, if you have or for many reasonable data encoding strategies. So by data encoding strategies, I mean what kind of these green gates, so how you design them. We can show that if you have E encoding gates, then we again get a covering number bound that's polynomial in E. Bound on the log of the covering numbers, that's polynomial in E. And we can use classical learning theory techniques to show that this implies a generalization error bound that's again polynomial in E divided by square root n if you train on data of size n. So the message is like similar. I want to again highlight like a possibly interesting special case. So before I told you if you have a poly-size quantum machine learning model, you're going to be fine. Now what this tells you is even if your quantum machine learning model is exponential size, you could still generalize well if the encoding part is sufficiently simple. Or conversely, you could also have a very complicated encoding part, but if the trainable part is sufficiently simple, then you also generalize well. So that's why it can be, I would argue, insightful to look at trainable part and data encoding both. Yeah, so this is kind of what I've done in variational quantum machine learning. This first question I've already touched upon. So I think it's very interesting to understand when machine learning models outperform these bounds. And in my work with Robert Huang and et al., we have some initial numerical experiments where we see that the experiments outperform our bounds. But for generalization bounds, that's always hard to say because they're worst case over all possible distributions, and you can't test all possible distributions. So that definitely needs more investigation. What I personally also find pretty cool is works that take a more unified perspective on encoding strategy, trainable part, and measurement. So I've regarded them as like separate parts of the circuit, but you could also look at the circuit as a whole. They're like papers by IBM Quantum and also coming from, I think, Leonardo Banchis in Pisa, who make some initial attempts at this.
Describe a little bit what those guys are doing.
Which of the two?
Whatever you find more interesting.
So what Leonardo Banchi and co-authors do is they try and use, instead of like classical learning theoretic complexity measures, they try to use quantum information theoretic objects. So something like how much information does the quantum state that your QML model outputs give you about the classical parameters you gave in, or something like this. So they get bounds in terms of mutual informations and stuff like this. And there's by now like a relatively rich classical learning theory literature on information theoretic generalization bounds. And I think there's still like room to do this in the quantum world as well. All right. Yeah, what I think is also interesting would be to understand how to tighten these bounds for more restricted near-term devices. So the obvious way of how these bounds become better for near-term is because in the near term you have few gates. So the bounds are good because they depend on a number of gates. But I think that there should be other features of near-term devices that play a role here.
Can I ask a question? Maybe that's a bit of a stupid question also. You know why this is a stupid question in this specific context. I will ask this nevertheless, but we probably should discuss this when you're here. But there's no single such bound that acknowledges that the states will not be pure, right? I mean, it's one obvious and great idea to think of like short circuits and have like architectural constraints of various sorts. Wonderful, but that's much easier to address than having like layers of noise in between. And this hasn't, for good reasons, not really been studied much. But that's a true statement, right? There's not a single statement of this kind out there.
So our bounds in principle also apply to the mixed state case because they apply also to like circuits of CP-TP maps. So you could have like noisy gates, but we don't really care about what CP-TP maps. So you could in principle apply them, but they're not going to profit from this. There's one paper which uses Rademacher complexities, and they kind of look at how noise channels shrink Rademacher complexities. But I think this is more like an initial step. I don't think
no, but
complete
for
understanding.
the form, I mean like adversarial noise. I mean that you can't really choose the noise that you get. I mean just real noise, like the dirty noise. But the shrinkage is, that's the point. That's okay.
Yeah.
What is the
But I
paper
mean,
about the shrinkages?
Sorry?
Oh, what is the paper about the Rademacher complexities and the noise?
It's one of the group from, or Kaifeng Wu and co-authors. I don't remember which of the three.
Okay.
But I think it has noise in the title, maybe even. So if you Google like Kaifeng Wu and Rademacher complexities, you'll find it.
yeah, but I mean, Matthias, I mean, shouldn't this not be relatively straightforward? I mean, if you have like, I mean, you kind of have exponential noise dependence, both in number of qubits and depth usually. And I mean, you kind of, you shrink your space just like homogeneously, like
exactly.
these, like, and shouldn't that not be
easy? I think it shouldn't be too hard to incorporate this. Yes, I agree. No. I think it's like, so one thing that I personally would like to understand a bit better is whether the specific kind of noise you have matters a lot to this intuition. That I really don't know. And also something that I haven't yet looked at, which I don't have a good intuition about, is if you don't just have noise, but you also have architectural constraints, like which qubits you can connect and stuff like this, whether this matters for these purposes. That I don't know. Okay, and to end like with the dream, what would of course be super cool is to separate variational quantum machine learning from classical learning for a concrete task. But in my opinion, we're nowhere near, unless you say arbitrarily constructed tasks are also fine, because then you can take the factoring problem, or let's say the discrete log problem, and massage it into a learning problem. And then quantum machine learning beats classical learning for that specific problem. But yeah, I personally think there's still room to, or it would be interesting to find other tasks, let's say it is.
Yeah, I mean, you're also after like really practical things or stuff that you would be able to do with a NIST computer, right?
Yeah, that's true. That's a very good point. This discrete log thing needs a fault tolerant one. You're right.
Indeed. That's
I mean,
running short.
We should.
Yep.
I mean, we should also maybe, because we have these discussions like on I mean this stuff, and right now we also have one avenue which we're discussing, which is about like complexity of this device, or really computational complexity, and you know, defining like a complexity class that interpolates between BPP and BQP with a noise parameter, and I mean, maybe when you're here in Berlin, we can have a chat about this, and then cool. Because maybe something could fall out there, at least like morally or like by intuition, you know.
Yeah, that sounds good. Okay, so that's kind of what I wanted to tell you about variational quantum machine learning, and this is probably what most QML practitioners, if there is such a thing, are doing nowadays. But I'm not that connected to the practice side, so I'm not sure. So if you have other questions about this part of QML, maybe now is a good time. Otherwise, I'll change gears a little bit.
Maybe I can ask you to comment on the recent like essay by Maria Schult on looking for quantum advantages in quantum machine learning.
Yeah,
that's the wrong moment for this.
I haven't read it yet. I heard her talk about it, and well, okay, let me say it like this. I think that like studying machine learning with purely classical complexity theory is already in the classical machine learning world maybe not the best strategy. So I agree that it's not just like a computational advantage that you're after.
Okay.
But at least from the mathematics perspective, I still think it's interesting to look for these things. And I mean, for example, you might not need a computational advantage, but you could, how do I say this? You could think about what the possibility of a different type of data can give you as an advantage. So I'll come back to this later during the talk, actually. So whether quantum data helps you somehow more than classical one. And I think, yeah, I don't know, since actually I mean, quantum advantage maybe doesn't really just have to be from exponential complexity to polynomial complexity. If you have like a broader view of what quantum advantage can be, then I think it's still a valuable goal.
Okay, wonderful. That's a very fair answer. Yeah.
Maybe I can make a comment. I think that Maria's point, well, as I understood it at least, was that one should like focus on understanding these models without like always having the question in the back of your mind, like, does this model outperform a classical model or not? And I think everything that Matthias has discussed so far is exactly the type of thing that Maria would advocate anyway. Like none of those works make any claim as to like a quantum advantage or not. They just try in a genuine way to understand better the properties of these models. I think if I understood her correctly, that was more her.
Oh, I see.
Okay, yeah. Good, wonderful. Thank you very much, to both of you.
All right, then let me change gears a little bit and tell you about learning classical functions from quantum examples. So this is actually like the first paper that I ever wrote is about this topic, and I have a little bit of a soft spot for it. But I think it's fallen a little bit out of fashion, but I think it's still pretty cool. So first, let me tell you what quantum superposition examples are, because the idea is actually pretty simple. So if you have a probability distribution over inputs, P, and an unknown function F star, then classical training data was consisted of examples of the form xi F star of xi, where the xi was drawn IID from P. So now you can ask, how do we make this quantum? And one way of doing this was suggested by Nadab Shouty and Jeffrey Jackson in '98, so already like pretty early. And what they suggest is to basically use the weights of the probability distribution as amplitudes in a superposition. To get the right normalization, you take a square root. And then to superpose over the possible input-output states. So, okay, to make this reasonable, you should probably do bit strings, but the idea is, I think, pretty clear. And there's been a lot of discussion about whether this is a reasonable kind of example to consider. I don't really know. I guess for many purposes, it's probably not realistic, but I think it's a cool mathematical toy. And I want to show you a little bit what games you can play with this mathematical toy. So let's start with a very easy observation. Quantum superposition examples are at least as good as classical examples. Why is that? Well, do a computational basis measurement on the state you have in 4.1, then what you get is exactly one such labeled example drawn IID from P. So just by doing computational basis measurement, you can use such a quantum superposition example to simulate a classical example. And then the obvious question is, do you have a strictly better than, and not just at least as good as? And the answer, as so often, is it depends strongly on what you're considering. So I've compiled like some results that I'm aware of, and the first is a negative result due to Srinivasan Arunachalam and Ronald Wolf. Namely, what they show is that in the PAC setting, so in the setting I showed you before, where you want guarantees on that work independently of what the distribution is that you're trying to learn. And if you focus on the binary classification problem, then this does not help from the perspective of sample complexity. So let me slowly walk you through the table. So if you look at the class of binary the task of binary classification, and you try to learn a function class f, then the sample complexity, so the number of training data points you need, scales with the VC dimension of f. So this is like classical learning theory complexity measure, plus logarithm of 1 over delta divided by epsilon or epsilon squared, depending on whether it's realizable or agnostic. These are maybe not so important details. And what they show, and this is like after a lot of prior works also, so it's not just them, is that in the classical case, you have exactly the same sample. In the quantum case, you have exactly the same sample complexity as in the classical case. So in other words, the number of training examples you need differs by at most a constant factor, a universal constant factor, independently of whether you're using like classical examples or quantum superposition examples. Well, that's a bit disappointing. So from like the sample complexity perspective, you don't gain anything in like PAC learning. There could be a computational complexity advantage for specific tasks. These results don't rule that out, but I'm not aware of anything. So I think this is just like not yet understood. Okay, so you might now feel a little bit down about these quantum superposition examples, but fortunately, there's also some good news. So here I've compiled some of the good news. So there's a very, very simple problem that I've taken a liking to, namely learning linear functions. So here I mean learning Boolean linear functions. So it's just really, you take your input bit string and take an inner product with another bit string. So it's a very, very simple kind of function. If you try to learn this classically, then the number of samples you need scales linearly with n, so with the length of your bit string. That's basically because a single example gives you information about only one bit of your string. So the number of examples you need scales roughly like the length of your string. Now, if you have access to quantum superposition examples, you can use the Bernstein-Vasirani algorithm for quantum Fourier sampling and get rid of the n dependence completely. So this is an improvement from, I mean, sample complexity linearly in n is not a bad sample complexity, but sample complexity completely independent of n is much better. And this is not only the case for linear functions, but you can also go from linear to like, if you think in Fourier representation, linear is like a single Fourier coefficient that's non-zero. And now if you look at Fourier sparse functions, so you have like k non-zero Fourier coefficients, you can again get rid of the n dependence that you classically have at the cost of slightly improving the k dependence. But mostly you focus on the n dependence and think of k as constant. So that's quite nice. This is a result by Arunachalam et al. And I've forgotten who the et al. Are. Yeah. And you can also look at the problem of learning disjunctive normoforms. So this is like something that computer scientists find cool. And classically, there is no known algorithm for doing this from polynomially many examples. The best I've found, at least, so maybe I should have written best known to me, is something quasi-polynomial, so n to the log n. But actually already in this Trouty-Jackson paper, where they introduced it, they showed that you can use this to learn DNFs from sample size scaling polynomially in n, which is like a strong result given that a lot of classical computer scientist research hasn't led to any polytime algorithm. So that like the takeaway message is, if you look at concrete problems, and all of these are learning with respect to the uniform distribution over all n-bit strings. So if you look at specific problem and fix the distribution, then you have a chance of improvements, and they often, in all of these examples at least, come from quantum Fourier sampling. And well, if you want, you can now wonder what's so special about the uniform distribution. At least that's a question I asked myself. And if you care about this simple problem of learning linear functions, and you now don't have a uniform distribution, but you have a product distribution. So that means your distribution is like, on each component, you have a certain probability of getting 0 and a certain probability of getting 1. And then you just have independent components. Then classically, you still have like this n, the linear and n dependence floating around. And in the quantum case, you can still improve it. If you have arbitrary bias, you can still improve it to log n. Okay, the bias isn't allowed to be full bias, but then you can't learn anyways. And if you have a weak bias, then you can actually recover the case of no bias, where you don't have any n dependence at all. And there's also a result known for DNF learning with respect to product distributions, where they So this is by Canade, Rocchetto, and Severini, where they essentially recover the non-noisy, the uniform distribution result. And here I actually don't know whether there's any classical algorithm for doing this. And this is, the way this is proved is by taking quantum Fourier sampling, which is per se for uniform distributions, and making it biased. So this is like a very simple tool, but it can already give you some nice results.
Sorry, I have a question.
Yeah.
So in order to fill in the blank, could you not just like use sufficiently many classical samples to simulate one quantum sample and then multiply it by that?
What do you mean by simulate a quantum example?
Well, I guess my assumption here is that like there is a straightforward way to simulate a quantum example using classical examples.
Okay.
Like there is a translation from basically like a quantum sample to a large number of classical samples that's like polynomial or something like that.
Yeah.
I mean, I think this is
I'm not
exponential.
sure.
Yeah. Like, I mean,
yeah. I mean, the quantum example kind of has all the possible bit strings and their labels in it. So to simulate it classically, you might really have to see all of them, or at least very many of them. My intuition would be it's exponential, but I don't know.
Oh, I see. But maybe for certain probability distributions, it's like actually
not
exponential.
Sorry, Ryan, I cut you off. Do you have more insight?
No, I think what you said is exactly right. If P is the uniform distribution, then you like to get the exact oracle, you need exponentially many. But I think this is actually like a really interesting open research direction, which is for which problems and for which probability distributions does an approximation of this 4.1 state from polynomially many classical, like for which problems and probability distributions does a state like 4.1, but supported only on polynomially many basis states, allow you to still solve something? Like it's not clear that there's not problems where you can do something.
That's a good point. But the setting considered by Terry and co-workers, I think Grover. I mean, that's not so obvious. Like in what context that would naturally appear, right? Where you really have a classical knowledge about the probabilities, but you want to prepare the states in the Q sample oracle, right? I mean, it's a well-defined problem, but it's not so natural as a setting, is it? Well,
I mean, like if you consider the distribution independent setting, like let's say you just only care about learning with respect to the uniform distribution, which is something people care about.
Then of course. No, but I mean for specific P.
Yeah, I guess this is like a criticism you could also make of this, right? You sometimes assume the underlying P to be known in advance, and where does that come from, and so on.
Yeah, I'm not being critical. I'm just basically asking.
Yeah.
Also the Terry paper is a good paper. It's an interesting construction. I'm just wondering what context that would be relevant. Okay, wonderful. Thanks.
Sorry, one question. So you said that aside from the fully biased case, you have the same complexity.
Yeah, that's right.
Okay, so it's only that particular value for which you.
Yeah, the fully biased case is annoying because then you can always only learn one bit of your unknown function, or like of the unknown string. But other than that, it works. I'm hiding some details on the rock here. Like there are like prefactors that depend on how strong the bias is.
Okay.
I'm hiding those.
But that will always be upper bounded by n, right?
I guess
so
that depends on how you define the bias and its strength. I don't remember whether you could always upper bound it by something. I'm not sure.
Okay.
It's been too long since I've done this. Sorry.
No worries.
I had this one question, sorry, Matthias. In 4.1 state, when you construct, if you go back, yeah. So I'm assuming the probability distribution is unknown, and then to make this state, do you subsample to calculate these PFXs?
Yeah, that's exactly, I think, one of the reasons why this has become a little bit unfashionable, because it's not so clear where you get the state from. So in like the results I showed you, the idea was always there is some oracle that gives you the state, and then you work with the state. But I haven't really talked about how to create the state, and honestly, I don't know too much about this. But I think that, or from what I've read, it seems that many people are struggling finding a good justification for where you should get the state from.
Or could you just also not assume an oracle and say that the given complexities that we have at the moment, you just sort of inculcate somehow the subsampling complexity where you're sort of estimating these p of x's for each x, where you subsample
it's not so much about p of x. I think it's more about the f star, I would say. Because p of x, like you can think of p of x as just like uniform distribution. So 1 over 2 to the n for all x. At least for many interesting cases, that's what they looked at. But the f star is, I think, more the problem.
But wouldn't f star be just the unitary corresponding? Okay, we don't know the unitary. Fine.
Exactly. Yeah.
I think that the best motivation for this oracle is from cryptography. Imagine you have some like quantum communication channel, and it like is implementing some like crypto construction, and you have Alice on the one side and it's trying to send messages to Bob on the other side, and you can intercept this channel, but it's a quantum channel. Like then you in essence are sampling from some function, and let's say if you could learn the function, you could decrypt the message. Like if you have the ability to like send states through this channel, then you could like send in a uniform superposition state, and what you would get out would be this state 4.1. So I think that like this is most naturally like motivated in the context of this post-quantum cryptography, when you imagine having cryptography on quantum communications networks that you can like adversarially query with superpositions, uniform superpositions. And then you would get out like exactly this state, but with the uniform weight. Yeah.
Indeed. I mean, that's really a wonderful point. But that also tells us once again that this setting for the uniform weight is much easier to motivate than this setting for arbitrary p.
Yeah, probably true. But even that seems interesting for cryptography people. So like the problem of learning an unknown linear function is obviously a very easy one. Classically, this becomes super hard if you have noise. So this is called learning parity with noise, or learning with errors, I think, LWE. And the hardness of this problem is like an assumption that's often made in cryptographic protocols, so that it's hard to learn a linear function from noisy samples. And there's a nice paper by, or there are actually two, one is by Cross and Smith, and one is by Grillo and Karenidis, who show some noise robustness of this quantum way of learning linear functions. So if you have like noisy versions of this quantum example, you can still do it, and it's actually still pretty easy. So I don't exactly know what this means for post-quantum cryptography. I don't think it breaks any of the protocols that are out there. I think it's more like you have to be careful where your data might get intercepted, like Ryan said. So you don't want like a superposition state to get intercepted, because then your cryptography might become easy to break.
Sorry, could you just go back to the sample complexity bit for a second? I was just wondering, this prefactor.
Which sample complexity? This one?
Oh, yeah, in the biased case, yeah.
Yeah.
For values of bias that are not like fully biased, is this always like? Are you sure that the prefactor doesn't become equal to n? Like, are there values of bias for which the quantum sample complexity is larger than the classical sample complexity?
No.
No, okay.
Because you can always simulate the classical oracle by measuring the quantum oracle. So the quantum sample complexity is always at most the classical sample complexity.
Okay, cool.
Yeah, okay, I was gonna say something like, can you not also just see this as like a way, like a proof technique rather than something practical? Like maybe you want to prove some lower bound.
Sure.
And as you said, this is at least as powerful as any classical. So if it helps you to prove something in this model, like some hardness or something like that, then you know it works for
That's a fair point.
Yeah. Yeah, maybe I should have like when I said that I think it's become a little bit unfashionable, it's because like from a practical perspective, it's unfashionable. I think from a mathematics and computer science perspective, this is a perfectly good scenario to study. And maybe to like conclude my short discussion, okay, that wasn't so short, of this area of QML, what I've showed you is a lot of results where quantum Fourier sampling helps you a lot. And as far as I know, it's all quantum learning algorithms for this scenario we have are somehow based on quantum Fourier sampling. And as far as I know, they're restricted to what's called the realizable scenario. Personally, I'm interested in whether you can do this in the so-called agnostic scenario. And yeah, I've got some like weak agnostic results, but nothing for the strong agnostic case. And more generally, I think it's
Matthias?
Yeah.
This quantum Fourier sampling, I mean, what is it doing?
What quantum Fourier sampling allows you to do is to sample from the probability distribution that's formed by the squares of the Fourier coefficients of a Boolean function. And classically, to do this, you usually use a membership oracle, whereas quantumly, you're happy with a quantum example oracle. And that's why basically any classical algorithm that's based on Fourier sampling can be lifted to a quantum algorithm where you only need quantum examples and not membership queries.
Okay, nice. I mean, is this limited to like a Fourier transform on bit strings, or could you think about like Fourier transforms on other domains?
You can do other domains. People have done this actually. So for example, these results about the learning with errors problem, they are not about over F2, like not over 0,1, but over FQ for some prime Q, and you can still do it. So I think that's probably not an issue, extending to other, at least to other finite fields. Not sure about other fields.
So I have a question. Do you know if classical Fourier sampling works for classical agnostic learning?
No, I don't know. Wait, sorry. Sorry. There's a nice paper by Vitali Feldman about this. So classically, to do quantum Fourier sampling, you already assume quantum membership query. Classically, to do Fourier sampling, you already assume membership query access. And if you have membership query access, then you can actually, in the agnostic case, still somehow simulate something else. So I don't remember all the details, but in the classical case, because you already start from membership queries, there is something you can do for the agnostic setting. But in the quantum case, if you start from examples, it's much less clear, at least to me.
Cool.
Yeah, so that's why I think another interesting question is here, can you actually do some interesting quantum learning without using quantum Fourier sampling? I honestly have no idea, but I think it would be cool to find out. And then all of what I showed you before are like sample complexity guarantees. Most of these come with some computational complexity guarantees, except for the stuff for general distribution independent Puck learning. There, as far as I know, no computational results are known. And then there's other interesting models like quantum membership queries that have been studied a lot, or quantum statistical queries. And these have like similar flavors of taking oracle models or like access to the unknown data that's established classically and quantizing it and looking what this can give you. There's some really cool results there.
Sorry, Matthias, in like this third point, the quantum computational advantages in QAC learning. There's this paper by Servedio and Gortler. I mean, they essentially put like factorizing into a concept class. And I thought the point of this paper was to give exponential computational separation in the distribution dependent setting where you know you can't have a sample complexity separation.
Yes, I think that's right. I don't understand the result too well because I'm not familiar with the cryptography that lies behind it, but I think what you said is correct. But I guess I'm again leaning towards less artificial concept classes. So whether you can do this for, let's say, simple geometric classes or something like that. But yeah, that's a very good point. There are some results about this. You're right. I was exaggerating. Okay. Okay, I think we still have a little bit of time for me to talk about like the third area that I'm interested in, namely learning quantum objects from quantum data. And like, okay, probably I should have said this earlier. Whereas the variational quantum machine learning, I mostly presented results that I have with other people. The section I just showed you, most was by other people, and in this section, this will be even more the case. So I will mostly present results from other people. Mm-hmm. And so I hope you have a little bit of deja vu, because this slide is very similar to the slide you saw before. So a classical example was drawn IID, where inputs were drawn IID from P, and then you had the label. And I asked, how do you make this quantum? And well, before I showed you the quantum superposition example, there's a different, relatively straightforward way of making quantum using CQ examples. So classical quantum examples, which makes sense if you look at CQ channels, so state preparation procedures. And this is something I looked at, and also something Kai-Min Chung and Hans van Lin looked at. And it's a little bit artificial, but I think it still has a good justification. So what you do here is you assume that you still have classical inputs, but now you have quantum outputs, so state preparation procedures. So you imagine classical inputs are parameters of some, I don't know, knobs in your lab that you can tune. And the outputs are the quantum states that the state preparation experiment produces. And now a classical example would be basically the same as before. So like the xi sampled from P, but now, and crucially, this f star of xi, the output of the function, is not a classical description of the quantum state, but it's a real copy of the quantum state. And in that sense, this is different from what we had before, because now you just have a copy of the state. You don't have full information about it. So in that sense, with this scenario, like this makes examples quantum in a different way from what we had before. And yeah, I was wondering what you can do with this. What I looked at was doing binary classification in this case. So where the labels are not 0 and 1, but are like two quantum states, sigma 0 and sigma 1. So what can you do? And actually it turns out that this is pretty simple. Namely, the sample complexity here is this expression, which you might recognize from what we had for PAC learning before. So this is exactly the same sample complexity as in classical PAC learning. And this is maybe not so surprising. What I showed in my paper, and what I think is kind of cool, is that the strategy for achieving this optimal sample complexity is very simple. It's a semi-classical strategy, by which I mean that the strategy really is you first perform a simple quantum measurement you first perform local quantum measurements. So you measure each of the quantum labels separately. That gives you classical data, and then you process that classical data. So it's a very, very simple way of processing the quantum data that actually already brings you to the optimal sample complexity here. What I just want to mention is that you might say that this restriction to two quantum states is very artificial, and I agree. The work by Chung and Lin have something more general in that respect. They allow for more output states, but in contrast to my work, they have to restrict everything finite, whereas mine doesn't have to be. So
I have a question.
That's a trade-off. Yeah.
So why doesn't your measurement like have to depend on like how far away or how distinguishable the two quantum states are?
Oh yeah, sorry, I was hiding that under the rock. So you're right. There's some like the measurement you make to get this optimal thing is the Holevo-Hellström measurement for distinguishing the two states. So yeah, that dependence on the states comes in.
I see.
And but I think the distinguishability actually doesn't appear in the bound. I'm not sure anymore because it appears in the realizable case, but not in the agnostic one. I think was a little bit confused about that myself.
Cool. And do you know there exists an extension of this for like multiple states? Or distinguishing multiple states?
So yeah, I think there is no result. Like I don't think there's a paper that does this. I think you should be able to extend my method, but I'm not sure if it's straightforward. Because so what I do is basically perform the measurement, then you get classical data, think of that classical data as a noisy version of some true data and use classical algorithms for learning from noisy data. And for learning from noisy data with like true labels, there are very good, like this is very well understood since like the 80s. I don't know so much about multiple labels. Okay, I'm not sure about multiple labels. I would expect that you get the same thing, but I don't know for sure.
And do you have an accompanying lower bound for your sample complexity?
Yeah, so that's why I write the theta here. I do prove lower bounds. So this is essentially tight. Now, the reason why I emphasized so much this semi-classical.
Short question, Matthias.
Oh, yeah, sure.
But I mean, I would intuitively expect this is just like, I mean, just like a harder version of the classical problem. I mean, you take something which have classical labels, and then you just like map the labels to quantum states, and then.
In principle, I agree. So that's again because I didn't show you the details. Like in the classical case, you really have to distinguish 0 and 1. In the quantum case, I measure your performance by the trace distance between the state you produce and the state you should have produced. So you kind of rescale your error depending on how far off you are. Now with 2 states, that's really just a rescaling of everything. If you now have multiple states, I'm not quite sure what effect that has.
I mean, could not do like the same in the classical case, which just say you predict not 0, 1, but 0.2, and then you take the trace distance between those two things.
Yeah, exactly. So I mean, that's let me see. Yeah, so in that sense, it's very similar to the classical case. I guess what you have to show for the lower bound is for the lower bound, you actually have to prove something because the kind of data you have is different, because it's like quantum data. So in principle, you could have like a weird quantum processing of the data, and that might give you an advantage over what you can do with classical data. At least I think so. And that's why I invested time in proving the lower bound.
Okay, but I mean, is there an advantage over like classical data, or?
Depends on how you formalize this. I would say no.
Because like, I mean, in the end, you have like the classical problem, but then you just like make your labels not perfectly distinguishable.
Yeah.
In your experiment. I mean,
yes, that's true.
I would think that can't make it like more efficient.
Yeah, I think I agree. In the end, I agree. Elias, should I address your question right now? Or actually, let me read it first to see whether I can address it. Multiple state. Maybe, I don't know. Might be worth trying out. Yeah, but so let me maybe, in the interest of time, continue. So what's the reason for my emphasizing the semi-classicality here? I emphasize this because there's a very nice result by Huang-Qing and Preskel that puts this in a like a broader framework. So, and I'm butchering the result. Like this is an extremely informal statement because I just didn't have that much space. So when you're trying to learn a function that basically has the form, you plug in some classical parameter into a CP-TP map that prepares a quantum state, and then you perform a measurement, and the function value is the expectation value of that measurement. And you try to learn such a function well on average. Then the optimal sample complexities for semi-classical learning strategies, where you basically do what I did before. So you have to perform a measurement on each single example you get, versus fully quantum learning strategies, where you could like access the channel E coherently, keep states in quantum memory, and therefore have some like more intricate processing. These optimal sample complexities are close in the sense that the classical sample complexity can be upper bounded by the quantum sample complexity times the log of the dimension of the involved quantum systems divided by the desired accuracy. So and this result even applies to like adaptive classical access versus quantum query access and classical post-processing versus quantum processing. So this is relatively broad. And it shows you that for a variety of tasks, if you have quantum data, you can, without much trouble, measure it right away, and then try and process it classically. And it won't cost you much on the level of sample complexity. And like my result is, I would say, a concrete example where I can prove that the sample complexities are even the same. For them, they're closely related at least. Now, there wouldn't be as much interest in quantum data right now if this were the end of the story, because there are also some separations. So the maybe I should highlight this. So the an important word here in my very informal statement is the on average. So the average performance is what makes this possible. If you focus more on worst case, then there are no separations. So I've compiled some of them, and all of them are very recent, and in almost all of them, Robert Huang was involved. So for example, and this is what they already did in their early work, if you want to predict the expectation values of all n-qubit Paulis, then classically you need exponentially many samples. So by classical, I mean like this semi-classical learner essentially. Whereas you can do this with just a linear number of examples. And then Robert and co-authors have some other tasks like distinguishing a depolarizing channel from randomly drawn unitary channels and so on. And in all of these cases, actual quantum access to the data and the ability to store stuff in a quantum memory helps you a lot on the level of, okay, here they call it query complexities because they think of it more like as interacting with the unknown process and querying it. And there are even some separations that take the size of the quantum memory itself more into account. So that was probably a bit too fast, but what I want to highlight here is that whether quantum data and quantum processing of quantum data has something interesting to offer really depends strongly on the questions you're asking. And I think these works are extremely nice examples, or giving extremely nice tools and examples to understand what kind of questions you can actually get something interesting for. But I also think that there's still more to be done here.
Sorry, one question.
Yeah.
The classical and quantum sample complexities. Does this work for any generic CPTP map? So like,
which of the?
So in the statement of their theorem.
Sorry, this one you mean?
Yeah. Like, does this work for arbitrary CPTP maps, or is there any restriction on the level of the map?
I think it was for arbitrary, but I'm not 100% sure.
That's weird.
What's your intuition? So
no intuition. It was just it just seems like a very strong theorem.
Yeah, I would say it is. So the way they do it is to kind of reduce the task of learning or related to a communication problem. So where you try to communicate which CPTP map it's about. And then covering numbers come in, but covering numbers should be nice even for arbitrary CPTP maps. So I don't know for sure, but I almost think it's arbitrary CPTP maps, or at least arbitrary classical quantum CPTP maps.
Okay, that's pretty impressive.
Right. So I think this is like quite an interesting subdirection of QML that's like just beginning to develop. And what I think would be a a good long-term goal would be more general insights into when fully quantum learning strategies can outperform these semi-classical learning strategies. So not only concrete examples of tasks where this is possible, that's of course also interesting, but maybe a more general understanding of what structures of the task make it possible for quantum learners to outperform the semi-classical ones. I think it's still there's still room for defining other quantum learning scenarios, so other ways of accessing quantum data and studying them in more detail. And something I haven't talked so much about is so in this table, the tasks that you see here sound like physics tasks, right? So it's predicting expectation values of observables or learning a quantum process. And there they prove some separations and query complexity advantages. So I think it would be natural to ask, what about tasks that don't look like physics already? So can you get advantages, or does it even make sense to talk about similar quantum versus classical query advantages for non-physics questions? But this is like
the problem,
open one.
The problem is kind of that, when would you have quantum states as data if it's like not a physics problem already, right?
Yeah, exactly.
That's a core question. The type of question begs for a physics question. Like, it's not very easy to see what a non-physics question could be not on physics.
Yeah, I completely agree with that, because you kind of have to motivate where your quantum data comes from. I'm just wondering whether there's something else we could do.
Maybe probably like what Ryan just mentioned, right? Like this crypto setting. There's like, where you have access to like an engineered quantum object that's not doing something a priori physically, right?
Yeah, exactly.
But can you not encode maybe like some like mathematical problem into? This is probably not what you mean, because that's again not very like a natural way maybe. But wouldn't that be some?
But you don't want to go. You don't want to have a detour over quantum settings when the problem is classical to start with. You would not encode it in a quantum setting and then take quantum measurements to learn something about that. The data must be like natively quantum, and that kind of asks for a setting where, well, the quantum data already come from a physics motivated situation somehow, because encoding is like cheating or not.
Yeah, I don't know. In variational quantum machine learning, they also encode, right? So
because they can't have coherent access to the data, right?
Yeah, that's true. Yeah, I don't know. Like, this is a very open-ended question that I don't know whether there's an answer to it. Let me just check. Did I want to tell you something else? No, now it's time for questions anyways. So feel free to ask even more questions. I probably won't be able to answer, but I'm happy to try.